questions below, and I'll respond quickly or in the next episode of Louis.
Hey everyone, we got some time to finish chapter 7. Time for to finish. Sure, that works. Let's put right here the timestamp 153. Stat 201, chapter 7. And this is quiz. Chapter 7 quiz, the New York something. New York data on initiative reports on annual water consumption. Now they get an R squared of this right here of 92.8. That means 92.8% of the variation in water consumption is explained by what year it is. Remember, blank percent of the variation in Y is explained by the variation in X. I want to point out you do have 3 interpretation questions on your test, R squared being one of them. You'll notice right here a negative relationship in the data, which means there is a negative correlation. The last question is where this really comes into play. Because if we have an R squared of, and you can turn it back to a decimal, 0.928. Now, when you interpret it, you turn it to the percentage. I want to make sure that's very clear that R squared normally is given as a decimal, but interpreted as a percentage. So you times it by 100 when you say 92.8% of the variation in the Y variable is explained by the variation in the X variable. Important for the test. So you can reverse it by square rooting it. But when you square root it, you have to realize you have to know if it's positive or negative. So if you look down here, it is definitely a negative correlation because square rooting R takes away the square and makes it back to correlation, which is 0.963. The rest of the problem is okay, not my favorite, but it's asking about what are the variables in the regression. It's going to be water consumption in millions of gallons per person. If you take a look right here, water consumption in millions of gallons per person right there is the variable, I believe, water consumption in millions of gallons per person. And what are the units? It would be millions of gallons per person per year. So as you change right here, it's like a decrease per year. Like how many millions of gallons is it changing per year? It's about an X versus Y problem. We got one wrong. No, it was the second one. No, I think we got the R squared right. No, did I get the R squared right? I did it. I did the mistake every student does. I'm a student now. Did you see it? Do you see the mistake? It's asking for correlation. It's asking for correlation. When you square root R squared, you have to remember that a number, when squared, loses its positive or negative. So when you square root R squared, almost like this is a test question. I did this on purpose.
Wow.
Owen Wilson's impressed. When you square root it, you have to look at it or look at the slope to see if it's negative. So this is negative because it goes down. It has a negative slope. And correlation gives direction. So the one error we made was on that. I did that on purpose. Let's do the next question. Okay, we have another fun one. Actually, it's one of my least favorites. We're doing all my least favorites today. Least favorite means that last part was applicable to the test, especially as I talked about in that problem, how to check the value of correlation, you'd have to either look at the slope or look at the model itself. I'm not a big fan of, like, what are the units of the problem? We've never asked a test question that say, what are the units of the problem? We do ask, like, what is the X, what is the Y, what is the explanatory, what is the response? This one I've made mistakes on because it says the predictor. The predictor is not what we are predicting. It is the X that predicts Y. So the predictor leads to the predicted, and the response is the Y variable of interest. We mentioned this in the notes. We call the X usually the explanatory. So when you're riding a roller coaster, you usually want to understand how long the roller coaster will last. And you want to understand how long it lasts, and what explains how long it lasts, how big the drop is when you go on the roller coaster. The drop is going to be in units of feet, and the response variable, which is the one we're interested in understanding how long is this roller coaster going to last, is going to be in seconds. 1 unit of the slope does the slope have? So it's going to be seconds per foot drop, I believe. Like seconds per foot drop. Like, is there an increase or decrease in how long the ride lasts per foot drop? So now you have to get into the idea of roller coaster physics. You never thought you'd be doing that in Stat 201. So let's grab roller coaster physics here. I'm grabbing a worksheet to draw and talk over some roller coaster physics. You'll see it in just a moment. Okay, so when you're on a roller coaster, you can be on a roller coaster like this. Whee! This is you on the roller coaster. There you are. You're all whee. Whee. Or you could be on a roller coaster like this. And this is where there might be divergent opinions. But the roller coaster with the bigger drop is probably going to go super fast and be super quick. The roller coaster with the smaller drop also depends on track length too, right? But the roller coaster with the smaller drop is probably like wee, where this one's going to go wah, really fast. Got to make the sound effects. So I think a bigger drop leads to shorter ride. Does that make sense? A smaller drop leads to a longer ride because the ride goes slower around the tracks. You can't go super fast around a track if you don't get that drop. So slope is probably negative because coasters with bigger drops, probably you see like bigger X, smaller Y. I think we've done anything right. It's one of those days. It can't be positive. I know it's not. My theory was wrong. It's one of those days. I'm just like, man, I've done this problem so many times, and I reversed the logic on it. One of my least favorite problems. I was like, it's this problem, no. Check out yesterday's video where we had no issues, and we didn't get the subjective questions of roller coasters and drop. And I do like doing these questions here, so if I do get something wrong, you can see it. The X and the Y variable are pretty explanatory right here, as in the X being the drop. And I guess, yeah, if you go on a big ride and it goes down really fast, I guess they're thinking if you have a bigger drop, it takes longer to lose the momentum. But usually you get on the ride and it like screeches to a stop at the end. Like you're like, and just like, a subjective question is the worst. Now we get to a not subjective question. Let's hit a home run right here. Let's do it. Let's get nothing wrong. Found the sun too much today. Stat 201, chapter 7. Gonna get nothing else wrong. We got those wrong problems out of our system. This question right here is best done using the applet we've created. So let's go grab the applet, which can be found under the modules. So you need to go over here to the modules, and under the modules, go down to chapter 7, and you will see the Regression Solver Pro. So go grab the Regression Solver Pro and download the Regression Solver Pro right here like this. And once you download the Regression Solver Pro, we're going to open it up, and then we're going to work with it. So it's opening up in the background right here. Enable editing, and let's take a look. So I do want to point out again that this is found under the modules. So it's found under the modules. You're going to take your data right here and copy it. Copy to clipboard right here. With copy to clipboard, hit Control-C or Command-C to copy the data. Now you're going to go back into Excel, and when Excel, just paste the data. Now we're going to do a trick right here to fix the values. You could actually, there's a lot of ways to do it. We're going to do it one way. They want the year minus the 1900. So we're going to write equals this cell minus 1900. You could have also done it by putting it in the X variable. And then we're just going to paste downward. Not like that. We're going to click at this bottom cell and do that. Now we're going to copy and paste, but when we paste, we're just going to paste the values. So that just pasted the numbers in there. It doesn't matter if we lose the formatting either. And you could always just do this by writing 65, 70, however you get the numbers there, you do you. So with this, we're now going to take the rate and drop the rate in here. And we now have the regression model over here. Don't worry if the color changes. Just make sure you put the first value into this row right here. And you make sure you have the X and the Y's in the right spot. And you get the regression coefficients after you enter in the data. You could also enter it in manually, but copy and pasting is a good way. You have to remove the 1900 because this is 1965 minus the 1900. And with this right here, you can see the intercept and the slope, all the information. So I'm going to put this over. Well, let's take a look at the data, though. When you look at the data, you can see it goes down as this goes up, as in we go to higher years, 1965 to 2015. You see as year goes up, Y goes down, which I think is like cycling time or something. I think it's, live bursts. So as year goes up, live burst goes down. That's not this. That's not this. That's random. And not this. So the answer is right here. And there's some aberrations where it doesn't perfectly follow it. We could even trace back to the third data point, and you can see the third data point is a lot lower than the others, and that's where you see this point right here where it drops down to like 14, where the next one's 15. So it jumps from 18 to 14 to 15. So you see 18, 14, 15, and that does follow the pattern with the third, fourth, and fifth point. So in general, it's been decreasing over time. Now we're going to go and get the following values. Remember, it is Y equals B0 plus B1X. So X is years since 1900. And so we're going to take and we're going to simply put in the intercept and the slope. Notice how these are B0, B1. And I'm just going to put this over here so I can see it while working with it. And I think I just copy intercept down to 2 decimals, rounds, and then slope right here. So the intercept and the slope, B0, B1. Make sure you know what B0 and B1 are. And there we go. Check to see if the model is appropriate. These are the conditions. QQ straight enough. No outliers. Plot doesn't thicken. And if it meets those conditions, it's good to go. And yeah, pretty much does. I mean, it looks like a plot that follows, if you look at the plot, it mostly follows a linear pattern. Those aren't big outliers. They're tiny. So I'd say for the most part, it's 2 quantitative variables. It's straight enough. It's reasonable straight. And we don't know about lurking variables. Lurking variables are variables outside of X and Y, like when you think about shark attacks and ice cream sales, summertime's the third variable because shark attacks go up during ice cream sales go up during shark attacks, but it's summertime really that increases ice creams and shark attacks. A lurking variable is like a third variable that you're not mentioning. We don't know about that. We don't have reason to believe it. What is the intercept? The intercept is when X is equal to 0, we expect Y to equal B0 on average. So it would be in year 1900, because remember, our data is set though so that 65 is 1965. So the intercept of this model is in the year 1900, we expect the number of live bursts to be 25.62 when we round it. So do remember, when X is equal to 0, we expect Y to equal B0 on average. So we're going to look for the right interpretation here. It'd be the number of live bursts in the year 1900. That's the only one that shows it. Oh, wait, that's the slope. Oh. For each additional year, so the slope has to have for each additional year, and I think it's going to be this one, the number of bursts per 1,000 that has been changing amount per year on average. For each additional year, we expect the number of live bursts to change by this amount. This is going to be the intercept, which it didn't ask for. It asked for the slope. I'm almost making another error. I think I saw I, and I thought it was intercept. So this would be the slope. For each additional year since 1900, we expect the live burst to decrease by negative 0.11 thousand on average. So for each additional X, we expect Y to increase or decrease by B1 on average. The table gives intervals right there in fives. It wants us to estimate what it is in 1978. Now here's what's great. You could just take your equation that you've written and plug 78 in there. Not 1978, plug in 78. Or you can go over here and just plug 78 into the applet. And there's the answer. I think it does want it in thousands, does it? Nope, it's giving it in thousands right now. So the answer is going to be this right here, rounded to 1 decimal, 16.7. So it does still want it in thousands of live bursts. It should say that. In 1978, it was actually this. Now, this is where it's very important. Let me take a screenshot here. You have to know the equation for a residual right here and how to get a residual. Residual is actual minus predicted. So when we do a residual equals actual minus predicted. The actual is this. It even says actual right there. So this is the actual. This is the prediction from the model, which came from y hat equals b0 plus b1x. And so that is the prediction from the model. And so we simply take right here and do actual of 15 minus 16.7, and that is equal to negative 1.7, which means the model is over this. The model predicted 16.7 up here, and it was actually 15, so there's a difference of negative 1.7. So there is a difference. So the model predicts more, because 1.7 more than what we have. The birth rate in 2020 is not actually there, so actually make that prediction. Now, 2020 is going to be 120, because it's 120 years since 1900. So there is the prediction from the model, and this is a small extrapolation. Extrapolation is when you predict beyond what the model has for data. So there is some faith in this prediction because it's not a very large extrapolation. You hear that X right there? That's when you go outside the X variable to make predictions. But how about 2050, which would be 150 years? Now we're predicting well outside the range of where we have data, and we get 8.5. And this is where we probably have very little faith because the model is predicting a huge extrapolation. So I would say there is no faith because something predicting this far out is a very big extrapolation. Whew, I got scared. This was a harder problem. We did it much easier. It's because none of it's subjective. Because it's a small extrapolation. You're going only just one period forward. That's a small. A big extrapolation is when you say we're in the year 2015, let's predict out 30 years, 35 years in the future. So that is a very good problem. We got a similar one here to finish off today. We'll have done all of chapter 7 quiz. We're almost perfect. Our brain had to boot up here. We're booting up our brain. And I don't even have the chat open. Gosh, I am so... No one's been here, though. Ah! It's one of those days. Oh, I got to go home and write a paper. Oh, it's not due till tomorrow night. I try to do everything one day before. It's a tip I tell students is always do everything one day before it's due. Because if you work on something one day before it's due and you don't finish it, you still have a day. If you work on it the day it's due and you can't figure it out or you're stuck or whatever, you're stuck. So always try to finish things one day before they're due. Then you have an extra day. Everyone wants an extra day. Someone says, I need an extra day. You say, I'm going to plan an extra day. That's the way I do it. I try to hold, I'm not perfect, but for the most part, I hold to that. That's why I'm doing my work tonight. Chapter 7 quiz, the last one. This is researchers collected data. They collected data. They're looking at the calcium in water and the mortality rate. And what we see right here is a pretty strong negative. And what do we mean by pretty strong? Strength is the tightness of the bands around the form. So this is a linear form. If you draw your model through here, and then you draw the tightness, it looks pretty good. A little maybe stronger at the end, but about the same, which we call about equal strength or plot not thickening. It's about as good of a model as you get. It's a negative, somewhat strong model that says at higher levels of calcium, which means harder water, because calcium is a mineral that gets in water, and you see it around your sink, you're like, oh, what's all this calcium mineral doing in my water? You get it. And so at higher levels of calcium, we see a lower mortality rate. So it's a very strong negative relationship. Towns with harder water tend to have lower mortality rates. Here is the information for the regression equation. It's important we know what we're looking at. In our class, there's only a few values of interest. The values of interest for our class are going to be the following: the estimate of the intercept, the estimate of the slope, and the significance of the slope. This value over here is is the intercept. This is the slope, and then this is the p-value of the model, telling us that this model is very statistically significant because the slope is unlikely to be 0. So all we do is we take right here and put in b0, b1. We actually have to put in the values, but that is the general form of the equation. The predicted value of y is equal to b0 plus b1x. So we take 1910 and we round to 3 decimals, 574, and we do negative. Do not forget negative because it is very important because this is a downward relationship. Interpret the slope in context. Well, we are predicting the mortality rate. So for each additional calcium, we expect mortality to decrease by 2.095 thousand people, what it is on average. So for each additional point in calcium, we predict a decrease in mortality. Remember, we're talking about as calcium increases, we expect mortality to decrease. And the coefficient of the slope is for each unit increase in calcium. Explain the meaning of the y-intercept of the line. This is when x is equal to 0. So when calcium is equal to 0, even though this says 75, I've had a lot of students be like, but it says, I've had a lot of students say, but it says 75 there. Well, that's just an arbitrary point where they stop drawing. The y-intercept is mathematically when x is equal to 0, at least when we talk about like the y-intercept of an equation. So when calcium is equal to 0, the model predicts that a town with 0 parts per million calcium would have a mortality rate of B0. And you also plug 0 in here and solve. That'll get this value, the predicted value. Keywords like predicted are in there. So there it is. And next we have right here, the largest residual is 96. Residuals are how much you miss by. I don't know if we still have our drawing. We don't. The largest residual of 96 might be this or this, one of these up here, because it has to be above the line by 96 units. Remember, a residual is how much we miss by. Residual is actual minus predicted. So you would have the predicted, which is the line, and you have the actual, which is the dot, which might probably this one, sure. And then you have its residual, which is how much we missed by, and they're saying this is 96 units above. So it's 96 units above its prediction. Positive residual zone is above, negative residual zone is below. Anything that is on the line has a residual close to 0 or at 0 if it's perfectly on the line, because actual and predicted are equal because it's what it was predicted to be. And so it is 96 more deaths per 100,000 than predicted. So 96 more than predicted. The hardness of a certain town is 165. Use this to predict its mortality rate. Well, we just plug in X. So you go right here. I didn't just misclick it, did I? For each decrease. Good. I've missed questions because I have clicked. I've like clicked back on the screen and like that right there. And I've missed a question. It'll be like, you're wrong. And I'll be like, I did everything right. Haven't done that today yet, though. So it said a certain town has a hardness of 165. So all you do is X is calcium. You put 165 right here. Or you go right here and you go 165. And then you just solve the equation. I mean, you're multiplying. A little multiply sign right there. And that's got it. So this will solve for the predicted mortality rate in hundreds of thousands. So 165 times 2095 and 1910.54 minus, there we go. And that's got it. So that is the predicted in 100,000. And it wants it to 3 decimals, so we should be good. Explain the R squared, blank percent of the variation in Y is explained by the variation in X. So 82.8% of the variability in mortality can be accounted for or explained by the variability in calcium. 82.8% of the variability in mortality can be explained by the variation in calcium. We should have 100. Got that 100. So I like these longer problems. They really walk through a lot of like find the intercept, find the slope. What does the slope mean? What does the intercept mean? This problem is, if you understand it, it's pretty much most of the chapter. It's about 80 to 90%. There's more versions of me doing this. I'm going to head off. I'm giving a test here soon. So I wrote a test last night. But with that said, bye for now, everyone. Bye.